Okay, thanks, guys. Yeah, so it's a pleasure to have Mike again. And, Sierra is, um, here to, as a part of our mission, educate as many designers as possible. That is not how we stay in business. We stay in business by building circuit boards and assembling them. And so that's what we do in Silicon Valley. And we've been doing it for many years. And we see a huge uptick in complexity of circuit boards as well as different materials that are coming into play, different, as all the designs are getting more complex and higher speed, our job, we're taking it upon ourselves to bring experts together like Mike and others to provide as much information to the community as possible. And we also have a Sierra Connect. I encourage you to join there and ask questions. But we're here to assist. So we definitely want you to ask questions. And if you have a need for a circuit board prototype or not, we would love to be able to manufacture that for you. So today's agenda is really about jitter, and what are some we have some causes of jitter, but really it's a lot about how to mitigate jitter and how to measure and analyze jitter, and that's where Mike comes in as well. So we are going to have a follow-up as to kind of going over more causes of jitter and a summary of this presentation. So as always, Lucy will send out the details. So basically how is jitter affecting your data transmission? So it's basically the deviation in the signal edges from their ideal positions, and this deviation has several critical consequences. You basically have sampling issues. You can have misinterpretation of the transmitted data or bit errors. You can have issues where jitter can also lead to missing or corrupted data at the receiving end, and Mike will go over that example as well. So the types of jitter in high frequency designs, jitter in the time domain can be categorized into two types. So you can have random jitter and deterministic jitter. So in the frequency domain, jitter is referred to as a phase noise, and this is critical in high frequency applications like RF PCBs. So phase noise can cause interference between adjacent signals as well, both at the transmitter and receiver ends. So what causes insertion loss in high frequency designs? Insertion loss refers to the signal strength attenuation as it propagates through a transmission line, and the signal attenuation is caused due to several factors. First is dielectric loss, where the energy is absorbed by the dielectric material. Next is conductor loss, which is mainly caused by the skin effect and trace resistance. And the last one is radiation loss, where part of the signal energy escapes into the surrounding environment. So we're going to do a demo. Is that right? Is Vandana on?
Yes, sir. So,
okay, I'll pass it over to you.
Hi, everyone. We have the impedance calculator here today. This tool supports 82 impedance models with multiple geometries. We see that we have the uncoated, coated, and embedded microstrip here, along with the strip line. And for each of these models, you can choose single-ended or differential pair here. Let's go with coated microstrip in a differential pair mode and click on this. So the basic and the composite structures are displayed over here. Let's go with the basic model for now. The tool is also integrated with the signal loss, crosstalk, and the S parameter calculator, which I will be showing to you in a moment. We also have different units system available for the tool in the form of a drop-down. Here we go. This is the unit system. Let's go with mils for now and start entering the input parameters, dielectric height of 3.348, for example. Let's go with 3.63 as the dielectric constant, a coating height of 1.5 mils. Coating height H2C is 0.5 here as a default value, but you can change it if you wish to do so. Then we have a coating height H3C. Let's go with 1.5 again. To calculate the trace width, we need to enter delta W here. Delta W is the difference between the top of the trace and the bottom of the trace. You can click on this help guide that displays a table that suggests delta W values based on their starting copper weight. You can use that as a reference. Let's go with 0.5 for now. Enter trace thickness of 1.45, a trace separation of about 7 maybe, and a target differential impedance. Calculate and click on calculate W, and the trace width will be calculated and displayed along with the other parameters here like the coupling coefficient, odd even impedance, mode propagation delay, etc. We can also do the reverse calculation where we enter the trace width and calculate the differential impedance. Then we have the signal loss calculator here for the same chosen model. Let's go with 0.026 over here as the dissipation factor, a frequency of 10, 6 as the surface roughness, which is a standard roughness for a foil. And let's go with 2 inches over here and click on calculate loss. And the signal loss in the output and even mode will be calculated and displayed. Now we have the S parameter calculator here. Let's go with the source impedance 50 and the load impedance 50 again. And you can select the output type. Let's go with complex for now and click on calculate S parameters. Since we have chosen a differential microstrip here, we can see that it's a 4-port network. So therefore, we have two matrices over here is the output, the 4-port S parameter and the mixed mode S parameter. The characteristic impedance and the propagation constant in the odd and even mode, both are calculated and displayed. One thing you have to make sure is to use the S parameter calculator, you have to make sure to use the signal loss calculator where we have entered the frequency, which will be used over here for the calculations. Similarly, we have the crosstalk calculator for this uh, model too. Oh, thank you so much.
Okay, thanks, Vandana. Let me go back to the presentation. Can you see okay? Can you guys hear me and see the screen?
Yeah, we can see.
Oh, okay, great. All right, so we definitely want to talk about strategies to minimize and mitigate jitter and insertion loss. So first and foremost, you have to select the right PCB materials for your application. And there are lots of materials around the world, and I think US manufacturers are becoming more accustomed to the overseas materials. So check with your manufacturer if they have experience with that material. Knowing the process steps of a material is critical in order to build a good circuit board. Anyways, I digress. So we want to first reduce the skin effect losses at high frequencies. So to do that, you can pick materials and copper foils that are specifically designed, for this purpose. Maybe they have a very low tooth profile and, therefore have been treated so you have good adhesion strength. But look at the type of copper foil that's being used in the materials, and I'm sure your fabricator can help you select that. If you don't specify anything, then you don't know what you're going to get. So as true always for PCB manufacturing, try and specify what you want without over specifying. So next, you want to select a substrate with high volume resistivity to minimize any leakage currents. And you want to choose materials, with a dielectric constant of less than 4 and a dissipation factor of less than 0.005. These are good, these would be good material selections. So next is, once you select your material, is to make sure you have a stack up, which is good, but also manufacturable. And that you'll know by talking to your fabricator. So you want to place your signal layers 1 dielectric away from the reference planes to enhance noise suppression and Next, you want to position your RF traces and components on the external layers, and here you can easily control trace width and space to ensure uniform impedances. And finally, you want to group your signal layers based on operating frequencies. So in one of our previous designs, we've isolated a 2.4 gigahertz RF signal and a 100 megahertz digital signal by placing the RF signal on the top layer and the digital signals on the bottom layer. So these are some good strategies for designing a good stack up. And if you have more complex features like buried vias or sequential laminations, it's really key that you talk to the fabricator that the material selection and what it's going to take to build that stack up go hand in hand. So the series terminations involve placing a terminating resistor between the driver and the transmission line, and the resistor is placed as close to the driver's side as possible, and its value is chosen such that the combined impedance of the resistor and the driver matches the trace impedance. So here we've shown in one instance where the driver impedance is 23 ohms and the line impedance is 50 ohms. To match these impedance, implement a series resistor of 27 near the driver end. Then you can have parallel trace transmissions, where parallel termination, involves placing a shunt resistor in parallel with the receiver. And this matching resistor absorbs all reflections at the far end of the transmission line. And you want to connect the parallel resistor to the power supply or ground plane, depending on the IC's internal circuitry. So here are some design tips to reduce channel effects. Again, Mike will be talking about the channel effect. To minimize jitter and insertion loss during signal transmission through a channel, you want to ensure consistent trace width, thickness, spacing throughout the signal path. And then you want to have thicker copper, which is generally translates to lower impedance. And when using two reference planes, incorporate stitching capacitors to ensure a continuous return path for the signal, and incorporate transition vias near signal vias where routing RF signals between layers. So next, decoupling capacitors. So you want to reduce your parasitic inductance and capacitance by placing the decoupling capacitors directly beneath the IC's power pin or right next to the pin. Employ capacitors of similar values in parallel to cover a broad frequency range. You can ensure that each power supply rail has its decaps, as different power rails may have different noise characteristics and current demands, as well as the other items on the slide. And then next, we want best practices to incorporate your guard traces. So guard traces, definitely shield critical traces, signal traces such as clock lines and RF signals from the unwanted noise coupling. So you place them around the sensitive lines and connect them to the ground plane or a dedicated reference voltage. This will provide low impedance path for any coupled noise. And you want to keep a consistent distance if you can, 3W to 5W between the guard traces and the critical signal traces. Not always possible, but if you can, you should do that. In terms of back drilling, to reduce your via stubs, a via stub is basically an inactive portion of a via, and it can this acts as a resonant circuit at specific frequencies, creating impedance mismatches for signals operating at those frequencies or their harmonics. So to mitigate this, you can employ back drilling. And right now the back drilling machines are really, really accurate. Both in how much bigger they need to be than the original drill and plate, and how accurately they can stop. All this is, pretty amazing new equipment. So you can talk to your fabricator on what their back drill DFM rules are, but it's definitely a good solution to reduce the number of laminations in your build. I guess we have another demo, stub length calculator.
Yes.
Okay.
Hi again. We have the maximum via stub length calculator now, which helps to determine the optimum stub length and its resonant frequency. At resonant frequency, the via stub functions as a resonant circuit and it can store maximum energy. Hence, the length of the via stub should be within an acceptable range to avoid signal integrity issues. So here we have two calculators incorporated in one. We can calculate the maximum via stub length first by entering either the maximum data transfer rate or the fastest signal rise time or the maximum frequency content, or the other where you can calculate the maximum frequency content when you for a given maximum via stub length. So let's start by entering a dielectric constant, and we can choose one of these options from the drop down to decide which parameter we want to enter. Let's enter maximum data transfer rate for now. Let's go with a value of 7 Gbps and click on calculate stub. We see that the maximum frequency here is 25 and the maximum via stub length is 33.3. Uh, Similarly, we can go to the other calculator. Let's enter the similar conditions here of dielectric constant 4. And let's enter maximum via stub of maybe 41 mils and click on calculate Fmax. So we see that the maximum frequency content is calculated here of about 20 gigahertz, and the other parameters are also calculated and displayed. So as observed at higher frequencies, for example, at 20 gigahertz, the via stubs are smaller and can cause serious signal integrity issues. So these are the kind of things that we can take care of by using these calculators. Thank you so much. Thank you for your time.
Okay, thanks. Okay, so of course, grounding is super critical. Proper grounding is crucial for maintaining your signal integrity and minimizing interference. So design a continuous ground plane with no breaks. That's the best to avoid impedance discontinuity. If you do need to have breaks, you can implement stitching vias along the edges of the ground plane or around RF traces. And you can have a via to via gap around lambda by 20 and or lambda by 10 to avoid overlapping and interference. And use top and bottom ground pores in your RF PCB layouts. And the spacing between RF traces and ground pores should be 1.5 to 2 times the trace width. These are all good practices in designing copper pores and ground planes. You can also have shielding strategies to prevent interference. So you want to enclose sensitive circuits to effectively block external EMI. You can use a Faraday cage to shield RF components or sections. You can create via fencing by placing a network of vias above and below the RF traces. And for strip line structures, you can ensure they're grounded through the top and bottom ground planes. When you're working with microstrip lines, the situation is slightly different since the top side lacks a ground plane. Connect the via fencing on the top layer using a trace. Here are the references to our blogs. And, with that, I will pass it over to Mike.
Thank you, Amit. And let me switch over to my stuff here as quickly as I can. Got to find the button here for it. Where's the share screen? And this one here. Hopefully this works. You all see that, right?
Yeah, looking good.
Thanks. Sorry about that. Okay, so I'm going to just shift gears a little bit into the measurement side of things. So Rohde Schwarz, we've been around for kind of a long time, about 90 years or so. We're in the test and measurement business. And for those of you who don't know us, we have a broad range of instrumentation for measuring RF microwave, radio testers, oscilloscopes, power supplies, pretty much a full line vendor of test instrumentation. And today I'm going to focus a little bit on one measurement, that being measuring a specific type of jitter, that being data dependent jitter, which is really sort of the subject of what we were talking about with routing and PCB trace design. So kind of a typical scenario, what could possibly go wrong? You have a very high-speed transmitter chip mounted on a board somewhere, transmitting a signal. At the transmitter you've got a nice open eye pattern. This is the way we look at digital signals. It gives you a good view of signal to noise plus jitter as it propagates through either a PC board trace or even a cable. There's going to be some frequency dependent attenuation, which is going to, as Amit mentioned before, is going to affect things like jitter and amplitude of the signal. And then in some cases, when you get to the receiver, the distortion becomes so great that even a viewable eye that is something that is discernible is not necessarily there. And in those cases, there are equalization strategies and methods that can be used to recover the eye. That would not be the subject of today, but just to focus on the effects that the PC board trace has and how it impacts, in this case, timing jitters, what we'll focus on. So taking a closer look, the main channel-related effects, those that are signal effects caused by propagation through either a backplane or a cable or some channel, things like, for example, loss or attenuation, which we talked about previously, are the main results of the propagation. But there can also be reflections. Even if you do match impedances very well, there could still be reflections due to some impedance mismatches. And then in some cases with connectors, you might have even a bigger problem maintaining a consistent impedance across the trace. Things like ringing and overshoot can also happen, and these are often resonances that, again, occur usually from things like parasitic inductance and capacitance on the board that can actually result in ringing, because a lot of the digital signals have very fast attack on the edges, very fast rise times. So if you look at an ideal signal digitally coming out of a chip, it might be a perfectly square wave, as I show here with the blue. Obviously, it won't be perfectly square, but pretty good. And as it propagates, you're going to see attenuation, but the attenuation is not consistent across the waveform. It's going to vary, depend essentially on what the data in the channel is. And here I show a standard NRZ, or non-return to zero modulation scheme, where a 1 is a high and a 0 is a low. And this is pretty common in most digital transmissions. Areas of the waveform where there is a lot of high-low transitions, like, for example, a 1-0 data pattern, you're going to get a little bit more attenuation there and some phase shift compared to areas where you might have a string of 1s or 0s where the signal level doesn't change. In that section, you might have less loss and, again, less phase shift as well. At the receiver end, there is a detection threshold, and what we care about in jitter measurement is how much the signal timing moves relative to that threshold at that crossing point. So if we take a closer look at that, what we want to measure is essentially the difference between an ideal waveform that would not be attenuated versus the attenuated channel. And this is not the best diagram in the world of drawing, but it gives you an idea of what happens as the signal attenuation is higher in the 1-0 pattern sections. You're going to see a lower amplitude and a lower rise time as well. So effectively the crossing point at that threshold is going to shift, as a result of that attenuation and even potentially reflections. So what we want to measure is essentially that effect on our digital signal. And the tool that we use to measure timing error is a jitter measurement. And the fundamental jitter measurement we refer to as time interval error, or TIE. And by definition, this is the difference between the actual edge position, that is where the signal crosses a detection threshold, relative to some reference position. And how that reference position is derived varies depending upon the measurement. But in the case of TIE, there is always a reference edge. And if you're looking at a data signal, we would be interested in seeing a crossing time in either direction, rising or falling, relative to some nominal bit rate or data rate that we're transmitting. The ideal edge positions are often based on an embedded clock. In some cases, there's an external clock as well. The clock provides the ideal timing. These are not necessarily equidistant reference points, because one of the things we like to allow is on the receiver side is often subject of a phase lock loop to recover a clock from the data, and that loop will actually track low frequency variations in the timing. So fundamentally, jitter is a high pass measurement. It looks at variations of the signal that are relatively fast, higher frequency. So we just basically measure these timing differences, the actual signal crossing relative to the reference. And then we can analyze this like any other measurement using things like histograms or even a spectrum view, and we can analyze the variation. Now, in the jitter world, what we care about is not necessarily RMS like you would in a normal noise scenario, but rather in jitter, we care about the worst case or the peak to peak, which makes it a very challenging measurement because peak to peak has a lot of dependency on essentially the observation time and how long you want to observe the waveform. So in the industry, measuring jitter, we've come up with a lot of different categories of jitter. And the reason this is done is because jitter sources have different, for lack of a better word, probability density functions. That is, as you observe a certain type of jitter over time, will it grow continuously or will it have some fixed range? And so the jitter pathologies or components that have a fixed range are referred to as deterministic, but rather bounded is maybe a better word to refer to them as. And among those are things like so-called data-dependent jitter, which I have marked off in a box here. And that data-dependent jitter is the primary source of jitter caused by propagation through the channel. And again, this includes our transmission losses and things like that, frequency-dependent losses, absorption, and even reflections. As Amit mentioned before, on the random jitter side, there's actually a random component which is considered that it grows over time the longer you observe it, and that is the noise-like component of jitter. The larger challenge for high bitrate systems is typically the data-dependent part because that's where more of the layout becomes a problem, and as higher bit rates occur in systems, you definitely need to be more careful about those losses. Periodic jitter is actually another subject which we won't really discuss today, but that's also a very big problem, often caused by the power delivery network and oscillations that occur there. But for today, we're going to focus on data dependent. There's also a crosstalk component here, and this is often at high speed digital. You can actually have adjacent traces interfering with each other. This is also kind of outside the scope of what we want to talk about here, but that's definitely a very interesting and growing area of concern as well. So in measuring jitter, if we think about it as random, it's a pretty easy approximation. We can just say, hey, it's Gaussian, measure the standard deviation, and then whatever observation time I want, I can just use that number of standard deviations. And observation time is typically specified in terms of bit error rate, which is another way of saying, how rare is it for a timing transition to happen at a certain distance from its nominal location. And again, you want that distance to be less than half a bit interval or a unit interval so that you would not have any bit errors in that observation time. That's really why we talk about jitter in terms of bit error rate, because it's really an observation time that we're talking about. Well, a basic Gaussian model isn't very good because, unfortunately, if we assume that the jitter is Gaussian and then we just measure standard deviation, we can actually overestimate what the jitter is. So back in the mid-90s, Fiber Channel Committee came up with an interesting definition that allowed for the inclusion of a non-random or so-called deterministic jitter component to be added into the model. And so the model that's currently used is this one called dual Dirac, where you essentially have two Gaussian or a Gaussian with a certain standard deviation involved with a pair of so-called Dirac delta functions. And really, this is nothing more than a way of fitting a statistical model to the measured timing errors that we've collected as we measured all these time interval error values. So when you see in a data sheet an RJ value, it's really that standard deviation in the model that is computed from fitting the data measured timing errors to this model. And the deterministic part accounts for sort of the non-random part of the jitter. there's a lot of limitations to this methodology. One of the most difficult is how do you fit the measured data to the model? Well, the fitting is kind of a black art. There's a lot of detail in there that's not talked about too much, but it does definitely have a fair amount of error in that fit that can result in errors in the overall jitter measurement. And the other problem that you have with this, probably more relevant to what we're talking about here, is that deterministic jitter that comes out of this model doesn't really help understand what the true effect of the insertion loss of the channel has on the timing error. And that can actually be larger or even smaller than what is reported in this DJ number here. So virtually every jitter measurement instrument has a more in-depth analysis feature available in it, which allows you to actually measure individual parts of the jitter sources separately in order to understand the specific impacts. So for lack of a better way of showing this, is sort of a diagram of what I would refer to as a short-term analytical jitter measurement. So what you do is you essentially acquire a waveform in a real-time oscilloscope, typically digitize the waveform, stuff it in the memory, and then essentially measure the timing of the threshold crossings. And then this is all math after that. We can just take these threshold crossings and then apply a clock recovery algorithm to them to generate a reference. It's really just all a bunch of numerical math. And then we can compute these time interval error values. And then we essentially have a collection of measurements, which we can then analyze using histograms, compute cumulative density functions, do fancy scaling in order to derive, let's say, various jitter components, that being the random, deterministic, and the total jitter, which are often reported in many of the standards. The most important category that we want to talk about here is the data dependent part. And this part of the jitter in these traditional measurements utilizes a repeating data pattern to figure out what that data dependent part is. So you need some sort of a repetition in the data signal, that is the values of ones and zeros, so that you have some reference on which to compute the part of the jitter that is not related to the random effects or even the periodic effects that are asynchronous with the data signal. So how does this kind of look? Well, this is actually a picture of a diagram, essentially, of what it would look like. It's actually measured on a real signal, but we're just trying to show the methodology here. This is the repeating data pattern. So you can see it's like a 0, 1, 0, 1, 0, a couple of ones in a row, then a 0. And what happens is, as the transmitter, the digital transmitter, is repeatedly transmitting this pattern, we somehow lock the instrumentation into the repetition of this pattern. A lot of different ways that can be done. It can be done using software. It can be done using clock recovery methods, or even special triggers, or even by supplying a pattern clock to the instrument. However it's done, you want to make sure that you're locked into the pattern so that every time the same bit in the pattern comes around, you can compute or measure its crossing time. And so what you're going to see for each crossing point in this pattern is a distribution of timing errors around some mean value. And the mean value is different, obviously, for each crossing point in the pattern, and it very much depends on the channel characteristics and the data that's being transmitted through the channel or the pattern. And so having all of this information in the acquisition allows us to compute or measure the mean value of each crossing time. And then really to find the ISI, or the worst case jitter, we just simply find the maximum and minimum mean value error relative to the ideal location. And just on this diagram, in a little more detail, there's a clock that's shown in kind of a purple color. That's the actual reference clock derived from the waveform. You'll notice the reference clock also moves around a little bit because, again, we're tracking low frequency variation. And the nice thing about this method is it measures what is a very complex interaction between the channel and the data, and distills it down to a relatively straightforward measurement. The limitation of this, among other things, is, first of all, you need a repeating pattern. So you need to put your transmitter into some standard repetitive mode, which is not necessarily easy all the time. Very hard to do on live data, of course. And the other issue is the length of pattern that can be accommodated in this type of measurement is typically fairly limited. So you're not able to get hundreds of bits in a pattern because this pattern has to repeat many times for you to build up the statistics. And so typically you're limited to relatively short patterns. And what this causes is a problem in accounting for the entire channel length. So I put a number on here, 100 millimeters, which is about 20 unit intervals at 28 gigabits per second. So at a very fast signaling rate, even a relatively short channel can have a lot of bits in it at the same time transmitting through there. And you need to account for that. And so that's sort of major limitation with this approach, which is sort of the standard. There is an alternate approach that rather than relying on a repeating pattern and doing statistical analysis of the transition times, we have a so-called model-based jitter algorithm. And what we're doing here is all in an oscilloscope, of course, acquiring a waveform, but instead of just calculating the crossing point times, we're going to use the entire waveform. And what we do is on the left-hand side, and I'm not going to cover every block in here, but on the left-hand side, we do a traditional time interval error calculation. But then we also, at the same time, we decode the data bits. So instead of just measuring crossing times, we're actually going to derive what the bit pattern was, 1010, whatever it was, and we'll create an ideal waveform for that bit pattern, an undistorted waveform. And then we do a computation where we filter that ideal waveform through a step response filter. And the step response filter that we convolve the signal with is optimized to match what we measured, the waveform that we measured, relative to the ideal waveform. So we're essentially filter it to make it look like the measured waveform. And that step response that comes out contains all of the channel related effects. And so in a way, it's a kind of a way of measuring the frequency response of the channel without accessing both sides of the channel, essentially just by looking at the waveform. And from that step response, we compute what the jitter is, that is the data dependent jitter, how much of that there is. We can also, of course, using other parameters in the model, derive all of the other jitter components like periodic, vertical, horizontal, as well as random. And all of those things are part of the model. But the key thing in the channel here is the step response. So here's a kind of a graphical view of what it would look like. Again, at the input of the model, we derive the signal values, the numerical bit sequence, and again, show this black ideal waveform. And then there are two step responses that we need to convolve. One is a positive going, one is a negative going step. And both of those are convolved with the ideal waveform to match what we actually measured. And so this has the benefit of using all of the information of the waveform, not just the timing information. The signal model looks like this. This summation down here, a lot of stuff going on in here. The step responses are right here, and they're convolved with each bit to make the shape as we measured. And then there is horizontal and vertical random components and periodic components, as well as the signal values themselves, ones and zeros. So it's a pretty big matrix inversion, but we sort of match the acquired waveform with the ideal and what falls out of these model parameters. So what does this kind of look like? If you were to measure a signal, and this is a 16 gigabit signal, NRZ, that's measured using this methodology. And there's a couple of different displays shown here, but this is actually a view of what the analysis software looks like. On the bottom left here is the actual step response. So you can see this is actually 50 unit intervals long. So we're 50 bits of acquisition from left to right, and you can see the rising edge. And then there's actually a wiggle here at around 937 picoseconds. That is, believe it or not, the SMA launch off of the evaluation board that I'm using. So you're seeing the signal coming out of the chip, and then there's the characteristic impedance ripple caused by the connector. And over here on the right is a transform of that step response. It's actually a magnitude frequency response of the channel. And again, you can see it's going out to about 16 gigahertz and then rolling off, kind of the bandwidth of the scope. But you can see the roll-off characteristic and even these ripples here in the frequency response, which are actually a result of that discontinuity. On the top right, we can actually derive an eye pattern, and the eye pattern is computed from the signal model itself. So this is actually an eye pattern of the model, but it reveals the data-dependent jitter, which you can see as these split rising and falling edges that are not touching. That's actually a result of the ISI. And then on the top left, we get, of course, the parametric views. But this view on the bottom left and bottom right, the step response and frequency response are kind of unique in the sense that this gives you a view of what the channel looks like after the transmitter has been soldered down. So you're actually seeing kind of a blind view of the channel without having to access both parts of it. And it turns out to be really useful for evaluating not just the board itself, but the entire system, and pretty accurately as well. So I guess the question arises, kind of how accurate is this? I mean, are we doing the right answer or not? So we did an evaluation to check and done this a few different times. And here's an example of a comparison. So we essentially have two traces shown here. On the upper trace is a magnitude versus frequency, and on the lower trace is a phase versus frequency trace. And what we did was we took a channel. This is an ISI board that is used for one of the digital standards, in this case, PCI Express. And we measured the channel using a network analyzer. And we also applied an 8.125 gigabit per second signal to the channel and then measured the step response and frequency response using this model-based jitter measurement. And so the blue trace in the background is the VNA measurement. As you can see, goes all the way out, 20 gigahertz. And the orange trace superimposed is this frequency response derived from the model-based jitter measurement. And you can see a very good registration all the way out to the bandwidth limit of the scope. In this case, we're 16 gigahertz with this particular scope. But also you can see there's a discontinuity that occurs right at the bit rate. So it's kind of a blind spot at the bit rate where the signal is actually transitioning, where we have some inaccuracy, but you can see that the overall trace is pretty good until you get to the outside the bandwidth of the instrument. And then down on the lower, you can see very good tracking on phase as well with that same discontinuity that you see at the bit rate. So higher bit rate would have a different discontinuity, different frequency. If we use 16 gigabits, it would be out kind of the end. But you can see it's actually, the model is very, very accurate way of measuring not just the data-dependent jitter, but also accounting for the reflections and loss in the channel, and being able to not just derive the measurement, but also derive the source of the measurement, which can lead to, things that you can look at to improve on that. So essence of a measurement is being able to show you a result, but also helping you point to a resolution of the problem. So just to kind of summarize what we said here, the channel insertion loss that we talked about, for example, S21 is one of the primary causes of data-dependent jitter, which is a very important source of jitter for high-speed digital applications. The timing error that you see is a result of both the data pattern and the channel length, so it's important to be able to account for both of those things. And magnitude and phase error is combined, so as well as reflection, so it's pretty complex interaction. The traditional methods that we use for jitter based on repeating patterns are very limited in the sense that they can't measure the underlying channel loss and reflections. They're essentially measuring the effect, but not necessarily the cause. And they're very limited pattern length and to relatively short channels, especially at high bit rates. And I should add that the model-based method allows one to measure the insertion loss directly by just accessing one end of the channel. And we can measure channels with lengths up to 200 unit intervals with this methodology. And there's no repeating pattern requirement. using the model-based method, it will work on random data in an active channel and makes it extremely flexible and helpful in tracking down and measuring these data-dependent sources of jitter. So that's all I got, folks.
Great. Thank you so much, Mike. That was great.
And any questions? Ooh, there's some long questions in there.
Yes, there's one question that's very long. Before we start the Q&A, I'm just going to do a very quick poll. And there you go. You should see 2 questions on your screen.
So you're saying the correct answer to that one is yes, right?
Okay, I'm going to leave the poll on so you guys have more time to reply. And in the meantime, I think we can get started with the questions. Mike, do you want to take the first one and the second one?
So how much improvement is in transmission is gained by using differential pairs? So differential pairs have okay. Can I just talk here or what?
Yeah. I'm just
okay, I'm sorry.
doing this to say that you are answering the question.
Gotcha. I cut this off. Okay. Yeah. So differential pairs. I mean, the primary benefit of differential pairs and the reason they're used quite often is they do reject common mode noise, which is important because a lot of interference, like switching power supplies and EMI and things like that, are in fact common mode. So the benefit of differential is really better signal to noise ratio and lower jitter. The question is how much. It very much depends upon the environment. So I don't know if I can give it to you in dB or anything like that, but definitely is the preferred way to do this sort of thing. I think differential, even especially at high bit rates, is virtually impossible to transmit data on a single-ended transmission unless you're using coax or a fiber. Trying to choose between. Oh, this is a definitely like an Amit question, I think. Between strip line and 16 gigahertz clock signal.
Yeah, I have to ask other experts at Sierra to give a good answer to that one.
Yeah, okay.
Big question. I will ask Atar to reply, and I will get back to you with an answer.
Yeah, it's definitely a good one.
We'll look into it, Kinmo.
Yeah, thank you. Yeah, that's definitely a pretty cool. Use 100. What was the frequency at which we are looking at insertion loss and by how much? We use 112 gigabits per second. What is the frequency at which we are looking at insertion loss and by how much? So, rule of thumb, you're going to look at the fundamental. Well, that really depends on 2 things. One is what is the coding. If we're talking 112 gigabit per second NRZ, then I think we are. That's something like a 56 gigahertz fundamental frequency. So insertion loss at that frequency is extremely important. It's 56 gig, but you're going to want to go out beyond that to understand what's happening. Certainly, rule of thumb is 5 times, but I think in a practical sense, I don't think you need to go that far. I think if you get to 100 gigahertz, you're probably good. But even 56 would be probably where I'd want to focus more than anything else. Accuracy of the step response method you showed depends on the load matching on the receiver side. Is that a potential weakness compared to normal pattern recovery method? Yeah, that's a good question. So the step response method, yeah, definitely depends on the load matching on the receive side, for sure. Most of the time we test these sort of things terminated into 100 ohm differential load that sort of matches the characteristic impedance of the transmission line. But the nice thing is it's not any different if you're trying to use the normal pattern recovery method. It could be the same either way. The normal pattern recovery method would, in fact, include the reflection effect of the scope input or the instrument input anyway, except for in the normal pattern method, you would not be able to discern the source because you would not have the visual and the measured step response that you get with this method. So yeah, I don't think it's a weakness there in that respect. Another side effect, by the way, of this step response method is it's extremely good at measuring what I would refer to as stressed eyes. So when the signal is extremely distorted, this method still gets a very accurate result. And that's mainly because we use all the waveform data. Here's a good Amit question, maybe, or maybe one for later about guard trace.
Yeah, so I think it depends on the design, of course, but 1/10 to 1/20th of the signal wavelength is the right, it's just kind of the rule of thumb.
And I guess what happens if a signal rise time exceeds 6 inches on a PC board? I think when that happens, you're probably working in lumped as a lumped circuit, so you probably don't have to worry too much about reflections or anything else. It's a little bit easier, I'd say. But I don't necessarily think that you would lose any cycles or anything like that. Oh, yeah, that's a good question. So at what bit data rate the traces need to be externally routed versus internal layers? I think it depends a lot on materials, right? I mean, it's difficult to say there's one particular data rate. But, certainly as you get above 100 gigabits, I'm sure it's almost impossible to keep it within layers.
Okay, great. Do we have any more questions?
So
Doesn't seem like it. Okay, well, thank you so much, Amit and Mike and Vandana. Oh, one more question.
Gotcha. I'm going to toss this one to Amit because this is actually a layout question. And we can feel free to answer that later too.
Yeah, we'll get this one later too.
Yeah.
We need more information about the design if there is one.
It does. Yeah. It's not a universal question, right?
Yeah, you have to know more about the design.
Yeah. He's just basically saying relative to the wavelength of interest. So he wants it in terms of wavelength, but.
So 1/10 to 1/20th of the wavelength.
There you go.
Okay, great. Thank you very much. Thank you so much, Mike, for doing this webinar with us. It was really great. And thank you, Amit, for presenting. Thank you, Vandana, for the demos.
Yeah, thank you, Irene.
Well, thank you all for your time, and hopefully that was helpful. I appreciate your time.
Thanks, Mike.
Thank you, guys.
Have a good day, everyone. Bye-bye.
Bye-bye now.